Okay, we're ready to make a start now looking at our next little section on the topic of superposition, and that is looking at stationary waves. Now, what I thought we'd do first of all is have a look at an animation that should give you some sort of idea of just how things work in terms of producing the standing wave. I like this animation. If we just start going there, we'll see a, a wave moving from left to right across the screen. Just while it's moving, there are some things that we can change. For example, we can hide or show the resultant standing wave. At present, we're looking at the incident wave coming in. As the wave heads towards this boundary, you'll see as soon as it hits the boundary, it will reflect. And when it reflects, it will be inverted. There'll be phase reversal on reflection. Let's just pause it for a moment there. We can start to see this area down here, where this part here, where the wave has now been reflected. Okay, let's just continue that on. Pausing it again to stop at that moment there. What we can now see is that the incident pulse, which is this red one, so we've now got the wave, well, there's this one red down here as well. So this red pulse is almost overlapped with the reflected pulse. And so what do we get using the principle of superposition? We get that shape down the bottom here. So we get a larger bit of the wave there. So let's just continue the thing on a bit further and hopefully just continue to observe that. And you'll see that as the blue reflected wave moves from right to left, it starts to interfere with the red incoming wave. And what do we see? Is we see being produced effectively now a stationary wave. We've got points here that are nodes. You'll notice that at those points, the particles, including this one here, never move. But there are other points here, 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 which are antinodes labeled A in here. And those are points that move with maximum possible displacement. They don't have that maximum displacement all the time, but they certainly display that. So we'll keep it going a little bit longer. You could take a note of the website, there's Walter Fent website, and download this animation yourself if you want to have a play around with it and try changing different things. If we turn the resultant shape off again, there are simply the two traveling waves, one traveling to the right, one traveling to the left, the progressive waves we call them, don't we? And what do we get as they overlap? We get the stationary wave being formed. Okay, moving back to our display here. Let's make it full size now. All right, so stationary waves. What is a stationary wave? This first statement here is really your definition. If you're asked to define what a stationary wave is, that is what you'd say. It's formed when two progressive, so that's waves that are traveling, they have to have the same frequency and really ideally the same amplitude, and they must be traveling in opposite directions. So a stationary wave is formed when two progressive waves of the same frequency, same amplitude, traveling in opposite directions meet. And just that point to note down here that with a progressive wave, we know that energy is transmitted, but with a stationary wave, the energy is not being transmitted, it is effectively trapped or stored in the vibrations that are happening. So I'd like you to note down underneath the heading stationary waves, then to note down the definition of stationary waves together with this other note down there. Right, we've got another little animation here. It shows much the same as the previous one, except I can run it within the notebook software. So once again, what we've got here is, if we look at it, we've got the red one being our stationary wave. So there are certain points, like that point there, and that point there, and that point there, and that point there, etc., that are never moving. Those are our nodes. And there are other points effectively here, 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 and that's the point that's up there effectively in the medium. There. Did I miss one? Yes, I did. One there, etc. One in there too. These are points that are moving with maximum possible amplitude, and those are our anti-nodes. Okay, so why is it that we get stationary waves, for example, in a string or something like that? So imagine we have, there's a fixed point, and there's another fixed point, and we have, oops, I should probably draw the string straight to begin with. We have the string there. We pluck the string, we displace the string away from its sort of resting position. And so what do we get? We get something like that formed, and then it'll be in that position as it oscillates back and forth. Okay, but what really is happening is that when we pluck the string, we send waves traveling through the string that way and that way. Those waves reflect off the ends, they come back, and effectively then we've got the waves traveling in the two directions in the string, producing our stationary wave. I think what you could do in terms of your notes is simply write that statement down there, but no more needed than that. All right, so here's a diagram that tries to illustrate in static form what's going on with our stationary wave. It's always much easier to see the animation and see what's happening sort of in real time, as opposed to trying to draw a picture of it here. Down the bottom, wave moving to the left, wave moving to the right, and then we've got the resultant wave. So what this is showing is at different points of time. So at t equals 0, in other words, at the beginning, we've got one wave there, another wave there, and that's the resultant waveform. And then quarter of a cycle later, t over 4, so t stands for period. So after 1/4 of a cycle, this is probably easier to follow, I suspect, than the first diagram. That's the position there of one of the waves, and that's the position of the other wave. And so what do we get as a resultant? We get the thing being instantaneously all flat. And then another quarter of a cycle later, the two waves have moved up to the top and down to the bottom. And so what do we get now? We get maximum displacement this way, whereas up here it was maximum displacement the other way. And then after another quarter of a cycle, we've got something similar to what we had up here, but this time the wave that was at the top is now at the bottom at this point over here, and the other wave, they swap places effectively. And what do you get again for your overall shape? You get a nice straight line through there. And then finally you're back to the beginning. T equals t is exactly the same as t equals 0. After one cycle, the thing has come back to its original position. So in terms of something to put in your notes, I know it's not as good as an animation, but you need some sort of a diagram to try to illustrate what's going on. So I'd like you to print that diagram off and pop that into your notes. And if you like, you could write some sort of a little explanation at that, describing it. And here is, if this helps you, is a little bit of an explanation then. Each snapshot is taken at intervals of 1/4 of the period. The resultant wave does not move along the string, it's a stationary wave. The frequency of the stationary wave is the same as the frequency, this is an important little point I think to note, the frequency of the stationary wave is the same as the frequency of the two progressive waves that make it up. We said in our definition of stationary waves that they have to have the same frequency. So if you had two waves, each with a frequency, let's say, of 25 hertz, one traveling that way and the other one traveling that way, then the stationary wave would also have a frequency of 25 hertz as well. So I think that could be put down there underneath the previous diagram.